Good morning, everybody. Welcome to this presentation of our paper, LaSS Running Latency-Sensitive Serverless Computations at the Edge. The lead author of this work, Bin Wang, was not able to record the presentation because he got a new baby, so congratulations, Bin. My name is Ahmed Ali Dean. I'm an assistant professor at Chalmers. Before that, I was a postdoc in Prashant Chinoo's group, who is the PI for this work at UMass Amherst. So today I'm going to start by giving you a little bit of background on serverless and function as a service. Function as a service is an emerging paradigm for developing and managing computations on the cloud. The idea is that you write code without worrying or thinking about the servers on which that code will run. You write code in the form of encapsulated functions that will just scale up or scale down, and you pay as you use. So once you start functions, you pay for their usage, and their usage is typically in the order of milliseconds or a few seconds or maybe a couple of minutes. But then once you stop to use the function, you don't need to pay anything. The good thing about this model is that you can scale from 0 to infinity, where infinity is basically, you know, uh, the a huge number of functions that you can run in parallel. Obviously, there is no infinity in reality, and this is supported as long as your server, your cloud provider has enough capacity, obviously. Then you also can scale to 0, which is a good thing because then you pay nothing. Basically literally nothing when you're not running anything, which means that you do not need to rent servers, you do not need to acquire servers on the cloud. There is increasing adoption by both academia and industry for this computing model. So we have AWS Lambda, we have Google Cloud Functions, Azure functions, IBM Cloud Functions. Oracle has their own version of this. So there is wide scale adoption now. So in parallel to the FaaS evolution, there is the edge computing and IoT evolution. And the idea of edge computing, as most of you would already know, is that we deploy a set of small-scale resources closer to the user at the network edge. This enables basically resource-constrained devices and like IoT devices and latency-critical workloads to basically be offloaded to these larger computational resources on the edge. Still, they are small-scale, but they are better than running on a drone or running on a camera, for example. There are a few challenges and requirements that comes with this evolution of edge computing. The first one is, how do we develop edge applications? I mean, one way would be to run microservices, to run traditional monolith. However, that wouldn't really fit the edge model. The other one is how to handle resource scarcity, because as we said, it's a small scale resources. So you have a bunch of servers, maybe in the order of 3-4 dozen servers, and you need to handle the scarcity on the edge when you have larger, workloads running or a huge surge in your workloads. And the third one is basically how to handle workload spikes. So you might get some parts of your application might become suddenly popular in a certain area, so you would want to scale up as much as you can. So basically, one idea is to run FaaS or serverless on the edge. And the good thing about FaaS is that it uses an event-based execution model. So once there's an event, you basically start a function and then you can start the processing. Since a lot of edge computations are bursty and event-based, so for example, IoT workloads. So if you have a motion activated camera, for example, then once somebody comes in the field of the camera, then you need to start the computations. So there's basically a lot of good points that would make these two a good match. There is also the scale to 0, which enables more efficient resource multiplexing in the FaaS model. So if you're on the edge and no one is using or no function is using these resources are kind of expensive because they're on the edge, they require higher maintenance and so on. So you can scale to 0 and save some power and energy and so on. And you can also scale to many functions rapidly, and since these are functions, that means that they typically require less computations compared to, for example, full-fledged applications. And there's better security because basically the function runs for a period and then does not run, which means that the attack time, the time available for an adversary to attack your system is much lower than if you're just running 24/7. So basically, now, given these two ideas, we decided to basically design a system, LaSS, that runs and manages FaaS on the edge. And in doing that, LaSS needs to basically solve the following set of challenges. The first one of them is that the majority of edge computations are latency sensitive. So a hosted function, these hosted functions typically run on containers. So a hosted function, when there's like an event and that requires computations, then it really needs to run as quickly as possible and get enough containers to meet SLAs. The second one is that since edge clusters are usually resource constrained, that means that there is no infinite scalability as you would get the notion of infinite scalability in the cloud. So overload is more likely to happen compared to the cloud. So LaSS needs to manage this. So two questions that arise are how to determine the right allocation for a hosted function and what to do during overload. And these two questions or these two challenges are what LaSS is all about. Now that I've given you an overview of FaaS and edge systems, let me basically give you the talk outline. So I'll start by giving an overview of the key features of LaSS. I'll then discuss the queuing system models that we use in our system and how we handle capacity shortages, and then I will briefly describe some of our key results in the evaluation. So we want to build a platform for managing latency critical workloads on the edge using FaaS. There are three key features to our system. The first one is that we use queuing theory based methods to determine an appropriate resource allocation for each hosted function in the system. Now, this queuing theory method works when there is room in the system. However, when there are overloads and there is resource pressure, we switch to a weighted fair share resource allocation method. And that is our second key feature. And then our third feature is that we have two resource reclamation policies for cases of overload. The first one is termination, where you evict some containers to make room in the system for other containers to run, for other functions to expand, basically. And then the second one is deflation. Deflation is basically a technique that we have developed in our group, first published in EuroSys 2019 and in HPDC 2020, where we basically work on instead of outright terminating containers, we basically reduce the resource allocation to these containers. So now let me basically describe the system model we use. We model each function as an MMC queuing system. MMCs are some of the most used queuing system models in literature. And the question, and the first M basically says that the arrival rate is a Poisson process. The second M says that the service time is distributed exponentially, and C is the number of servers / containers in the system. So the question that we are trying to answer is what is the right number of containers C to meet a certain SLO. And the SLO can be something like, okay, we'd like to keep the 95th percentile waiting time in the system to be less than 100 milliseconds. Queuing theory basically has lots of results for MMC models, and we use one of these. And the one that we use is that given C, it is easy to calculate basically the equilibrium distribution Pn. And that is basically if a request comes to the system and sees the system in state n, and state n means that there are n jobs in the system. These are the number of tasks or jobs in the system. The expected waiting time highly depends on how many jobs are in the system. So if the number of jobs in the system is less than the number of containers, that would mean that there are free containers or there are free servers in the system, which means that the incoming job can right away be scheduled on one of these empty containers. However, if n is greater than c, that would mean, there are no free containers in the system, and then basically the request or the job needs to queue in the system. And then queuing theory tells us that this queuing, the expected waiting time is n minus c plus 1 over c, the divided over c multiplied by mu. And mu is the average service time. Mu is the average service rate, and 1 over mu is the average service time. So we have our SLAs in the system in the form of the probability of the waiting time being less than or equal to a certain t. So the probability of the waiting time being less than, for example, 100 milliseconds should be greater than 0.95, for example. So this is this is p here is our bound on the probability. So given C containers, we can verify it can satisfy the SLA using this equation. We can calculate Pn using this equation, and then basically do a summation and make sure that we are always below than the bounding probability. So what we want to obtain is C here. So we came up with this algorithm to find the smallest t. We start with the current number of containers in the system for each function, and then check, are we meeting the SLA or are we not meeting the SLA? If we're not meeting the SLA, i.e. we have a higher waiting time, then for each function we monitor the incoming workload over an epoch of a few seconds. So say 2 or 3 seconds, and in that period, if we're not meeting the SLA, at the end of the epoch, we recompute the number of containers for each function in the system. To do that, we iteratively increase. If we're not meeting the SLA, we basically say, okay, now I have C. What would happen if I have C plus 1? What would happen if I have C plus 2? And so on. And we basically use this to, and the equations above, to basically try to find out when I start meeting the SLA, when basically this condition becomes true. And the least number of C that makes this condition true is the number of containers that I will need in the system. So once I converge to the required C, I start or stop containers for the functions that require capacity adjustments. However, what I described so far works when there's no capacity shortages. So when I have enough capacity for running all the functions that I want. And in some cases, the resources available on the edge can be insufficient to run all the functions as needed. So on overload, the above algorithm will suggest an allocation that exceeds the available edge resources. I cannot basically fit the number of containers suggested for the different functions on the current resources that I have on the edge. So we solve this problem using two techniques: fair share allocation and resource reclamation. Fair share is basically, the idea is that we require function owners to assign weights to their functions. These weights act more like a priority. So the higher the weight, the higher the priority, the lower the weight, the lower the priority. And then what LaSS does is that it guarantees minimum fair share allocation proportional to the assigned weight with respect to all other functions. So it's basically my weight. So the fair share will be my weight divided by sigma, summation of all the weights provided by all the other function owners. Obviously here we are talking about collaborative or cooperating function owners. We have a maximum, the maximum weight is a system parameter that is set by an operator. So if everybody basically comes in and says, well, maximum weight, that will mean that everybody will get equal assignment. However, it's more like the nice Linux values in this case. So we think that many users will be nice and will basically put a priority that corresponds to what the actual priority of their system is. Then the resource reclamation part, we have two techniques. The first one is immediate termination, where we basically, if the resources cannot basically support all the containers that are needed, then we resort to immediately terminating containers that exceed the fair share allocation of the system. Okay, and the other technique is deflation, where we shrink the resource allocation of functions based on their fair share allocation. And deflation is a technique that we actually developed at UMass and at Indiana, where we basically shrink resources when there is resource pressure and expand resources when more uh, um, when there is no resource pressure. So with this, I will jump to the evaluation section. First, let me describe to you how we implemented LaSS. LaSS is implemented as part of OpenWhisk. We added, been added over 2,300 lines of code and 55 files in OpenWhisk. He's the lead author and he's an excellent PhD student. Key changes to OpenWhisk using LaSS are first, in OpenWhisk, the control and data path are coupled. In LaSS, we decouple them. So as you see in the figure on the right, the figure above is the architecture of OpenWhisk. The figure below is OpenWhisk plus with our last implementation. So basically, this coupling of control and data path results in it being very hard to basically change or the allocation using our control our controller basically, or our methods using queuing the queuing models. So we decouple them. So now the last module has direct control over all containers in the system and can read arrival rate statistics from the load balancer. And based on that, basically, we allocate or deallocate resources to a function. Another major change is that we enable users to directly specify resource requirements for a function, which is surprisingly or not supported by OpenWhisk. For our evaluation, we emulate an edge using a 3-node cluster. The node has there are 3 standard servers with Intel processors and 32 gigabytes of RAM. And we basically then again implemented and adapted several functions to be basically to act as function as a service example. And these are the 6 functions. I think basically some of them are machine learning workloads, which are very popular in edge applications, and some of them are applications such as image resizing and geofencing and binary alert and so on. If you are interested in more details, please refer back to the paper. We actually have also open sourced most of our implementation. It became too cold outside for because Sweden, so I needed to come inside. So now that we have shown you how our system design is and the implementation, we'll highlight 3 key results. The first one is a validation of the queuing based models that we have. And in these 4 figures, we show 4 different configurations for different service rates and for different SLA objectives. We show that how LaSS basically maintains the SLA objectives for these 4 different configurations. To show that, we have a line graph showing the P95 waiting time versus the basically required SLA objective, which is the waiting time for on the SLA objective. And as can be seen that in all 4 graphs, LaSS is capable of keeping the SLO enforced. Now, we also show a box plot showing the different percentiles, the 75th percentile, response time, and so on, just for reference in these 4 graphs. So the first key result, while the queuing-based method is actually helpful in maintaining the request waiting time to below the required SLO. Now, the second key result that we would like to show is how the fair share resource allocation system enables the system to better utilize any free resources, but also enables the functions to expand and contract with their allocation. And here we have on the left a graph showing traces for the 6 functions we implemented. with different invocation rates, and these invocation rates are actually based on Azure, the Azure dataset, and you can read more about how we extract these these workloads from the dataset in the paper, and then we show how the two different resource reclamation policies we have work and would result in different utilization in the system. So the figure in the middle shows the termination policy results, and the figure on the right shows the resource allocation for the deflation policy. And basically, what you can see from these figures is that resource deflation, the deflation policy basically, enables the system to make better use of the white spaces. So there are much less white spaces on the right compared to the one in the middle. And white spaces are basically unused allocated resources in the system. So basically, in the deflation case, once a resource becomes unused, the system can quickly expand or deflate these resources so that other functions can make use of it, and hence provide better quality of service. While in the termination policy, you really have to kill the machines, and it's a bit worse in terms of how we can make use of the unused resources in the system. The third and final result is basically showing the scalability of our queuing based method, because we have this iterative algorithm. So one concern would be, okay, how fast can we basically do these calculations? And pretty much we were able to implement this system in both Julia and Scala. And Julia is much more scalable than Scala. That's one key result. And we're able to basically react to fluctuations in the workload using the Julia implementation within hundreds of milliseconds when the load doubles. When the load increases are more modest, so in the order of 10, 15, 20%, then we're able to react in tens of milliseconds. We note that this is as the number of containers increase, obviously the amount of computations that are required are much larger, hence the slowdown. Now that we have shown the evaluation, we conclude with basically saying that LaSS provides a good model for running latency critical FaaS workloads on the edge, providing latency guarantees and fairly splitting the resources amongst the different functions running. Now, the future work that we're working on is to include non-Poisson arrival and service rates in the models, so we get better accuracies, and to take composition of serverless functions into consideration when making scheduling and resource allocation decisions. Thank you.